All right, guys. Good afternoon, everyone. How are you guys doing? Doing all right? Free fam homework done? No. So that one takes a little bit more of time. Okay. When was it due originally? Friday? Tomorrow? Next Friday. Next Friday will be too much, but Monday. Okay. Monday night. Okay. Yes. Yeah. I think there are some small mistakes, and we'll talk about that. Okay, so let me turn this on, and we'll finish talking today about those Kirsch and fracture solution equations, and then we'll start talking about poromechanics. Okay, today is important that we start talking about poromechanics. But first, let's finish up with the Kirsch equation. So we started talking about cylindrical coordinates because Kirsch equations are developed analytically in cylindrical coordinates, not in Cartesian coordinates. And they are developed in that way because it's much easier to solve this problem in cylindrical coordinates than in Cartesian coordinates because of the cylindrical symmetry of the problem. I'm not going to write the Kirsch equations here. As I told you before, you can find them in the notes that I uploaded, and they are also over here. But however, it was brought to my attention by Jin that there is a small mistake over here. That exponent, I believe, it should be 3. Okay? Just double check your equations, okay? Just Google Kirsch equation. You'll find it right away. They are very well known. And just check for that exponent. So probably this one and that one. I believe that one. That one is 3 or 2. 2? Okay. And what else? Okay, but just check them again, okay? Just verify you have the right equations. I think this was done just by copying and pasting, and then Igor forgot to replace that exponent over there. I'm preparing also my notes, but I don't have them yet, in which I have the right equations, okay? So I'll see if I upload those as well, so you have another reference to check. But as I told you before, this is a very well-known solution, and if you Google Kirsch equations, you'll find them right away. Okay, there are a few things I want you to remember from this Kirsch equation. Of course, I don't want you to remember the equation by heart, but I want you to remember the main concept behind those equations. And the main concept behind that is what is called a stress intensity factor. Okay? So if I were to apply, for example, stresses in all directions into a solid that has a cavity in the middle, and let's say that I apply stresses, which are the far field stresses, and let's call it sigma infinity, which are the same in all directions. This is a plane strain problem, remember. If you were to solve the equations in Cartesian coordinates, you will see that these stresses, if you know, this is rock, okay, or a solid, and here there is nothing. Do you think the stresses can travel through nothing? No, right? So you will see that these stresses kind of like, in order to go around the cavity, they have like sort of to bend around the cavity, very similar to flow lines of fluid flow. But these are principal stresses lines. So here you have compression, and let's say they have a solid over there, it will be under compression. Similarly, if we analyze the stresses around the other direction, they will also start straight, and then they will bend. And when you get far enough from the cavity, they will be again straight. Well, first of all, this area where the stresses bend, that's the area in which your stresses change because of the presence of the cavity. Okay, that's called the zone of influence of the cavity. And your stresses around this region are going to be different than the stresses here in the far field. If you go to the far field, far enough from the cavity, you will see that your stresses are the same as the stresses in the far field. It's just going to be sigma infinity in all directions. But close to the cavity, those are going to be different. And if you were to solve the Kirsch equations, you will find out that the stress at any point around the cavity and on the face of the cavity is going to have a hoop stress, sigma theta theta. Remember, that's the tangential stress that is going to be equal to 2 times the far field stress. And what that means is that just because of the presence of a cavity now around this cavity in this direction, we have a compression which is twice as much as the far field stress. So we didn't add stresses to the far field. We just added the cavity. And because of the presence of the cavity, now you have 2 times the stress that you will have in the far field, even if you have, remember this, in isotropic stress condition. And in radial stress, there's going to be no normal stress, right? So for example, if you want to drill a wellbore here and you have this made out of sand, and you have here no radial stress and no effective radial stress and some finite effective hoop stress, that will fail the rock. So because of that, you cannot drill a wellbore in dry sand, or even with sand where there is no effective stress in that direction. If you have a solid that can resist having stress in one direction and no stress in another direction, then you can do that. We'll get later on to failure of rocks, so don't worry about that right now. Important thing over here is this intensity factor. Okay. And you will find that if you solve the Kirsch equations, you will see that that's the case. Let's do another case now over here. Let's imagine that now we have stresses just in one direction, and we're going to call it delta sigma. And we have a cavity. Very similar to the case that we discussed about before. If you have no stresses in this direction, if you just have stresses in this direction, your stresses again are going to bend over the cavity and go around it. There is going to be, very similar as before, a zone of influence. In the project, I'm asking you to find that zone of influence, but you will see it doesn't go very far. It goes about 3 diameters away from the wall of the wellbore, and after that, it's like there was nothing around in the rock. That's more or less the size. Okay, so if we had now just stress in this direction and no stress in that direction, You will see that now this stress intensity factor, let me write it down, intensity factor, which was this one over here. Now, if we look at stress right around here, do you think it's going to be bigger or smaller than before? I'm going to compare the sigma theta theta to the stress in the far field. It's going to be bigger, and it's actually going, what, it should be, okay, no, it's okay. It's going to be equal to 3. And you'll get that too from the Kirsch equation. So which means that if you had stress just in one direction, before we had in two directions, right? And that sort of compensates the stress in this direction. But if you had just stress in one direction, now we're going to have 3 times that amount at the face of the wellbore. So more stress anisotropy than before. And last, if we have, I'm going to just draw a section of it, but if you have a wellbore that is subjected to internal pressure, let's assume that the solid that we're dealing with is impermeable, so there are no fluids that can go through. If we have here a pressure PW, we're also going to have some stress intensity factor. But before I go to that, probably I was assuming something that was not very obvious. Is this hoop stress compression or tension? It is compression because I'm compressing everything. So this one is compression. What about here? Is this hoop stress at this position compression or tension? It's compression because, again, I'm compressing all of this, and these are lines of compression. But now look at this. I'm adding pressure here, and there is nothing around. What do you think is going to be the hoop stress? Now, it's going to be tension. It's going to be tension, and now the intensity factor is going to be equal to -2. Notice that these two are the same because these two cases are isotropic cases. So before we had isotropic stress around the solid, now we have a pressure which is the same in all directions inside the wellbore. And the wellbore solution, the Kirsch solution, how it is solved, I used to do this before, but it just takes a lot of time. And you can see it in my notes. It's just adding this solution to that solution to this solution. And as a result, you get the Kirsch equations. So let me go quickly. I'm going to fix those equations, okay? I'm going to send you the actual version. Here, this is the effect of isotropic stress. So S1 plus S2, that's that part of the solution. S1 minus S2 is that delta sigma. This is a deviatoric stress in the far field. And this term is a term of the pressure. And for example, for the hoop stress, you see they have also their own sign. And in this case, for example, this is negative. But that's it. The Kirsch solution is just a summation of these 3 solutions. And the important thing to remember here is this stress intensity factor. If you put a cavity in any place subjected to stresses, those stresses are going to amplify around the rock. So a rock that before having a cavity was stable and was not a failure, just by putting a cavity, you are putting more stresses on the rock, so the rock could fail around that cavity. And we're going to get later on in detail about failure of rocks. But for now, I like that you just remember, and you need this for the homework, that if we have if we have no pressure in the wall of the wellbore, if we have no effective stress, then you will have to check that. So let's say the PW is equal to 0. If PW is equal to 0, and that's what you have in your homework, it's just like a solid solution. If sigma theta theta is smaller than the tensile strength, what is going to happen? This guy here is tensile strength. So for example, here you could pressurize your wellbore so much that your hoop stress becomes negative and becomes even smaller than the tensile strength. If that happens, then you're going to have a tensile fracture, right? And on the other hand, if your sigma theta theta goes above the unconfined compression strength value, you're going to have here a shear failure, and you're going to have something which is called a breakout. We'll go, I repeat, we'll go in detail about that later on. And you will say, but if this is compression, why does he call it shear? Okay, we'll get into that later on, okay? But believe me for now that this is a shear failure, and this is the name of the failure type, and it's called a breakout. But just check the hoop stress. If hoop stress goes negative and goes beyond the tensile strength, you will expect to have a tensile fracture. If your hoop stress goes above the unconfined compression strength with no pressure, effective stress on the side of the wellbore, you're going to have failure of the material in shear in that section of the rock. If you solve this equation here too, you will see that in this case, so if I took another element, say over here, it will also be compression. All around, in this example, the wellbore, you have compression. But if you come to this place, because of the direction of the stresses, you will find out that now here you have tension. So this is where you will have a tensile fracture on the other side, and in this position is where you would expect to have a compression or shear failure. And we'll explain later on why I'm drawing kind of a triangle over there. Yes, Preston.
So assuming that kind of the top boundary and the bottom boundary, the displacements are equal to 0?
Not necessarily. When you add all of these together, you will still see that sometimes you find compression here and tension there. Or if you increase a lot of this one, you will find that it's easier, for example, to have tension over here.
So even if it's not combined on top and bottom, you're not going to get some effective displacement onto your shear?
What do you mean?
I guess like, if you assume the displacement on the top and the bottom are set to 0, then stressing it from the sides is going to create a stress in that kind of north-south direction.
Oh, if you're not letting this one displace, you will have a stress, but
Would it still be compression then?
I don't know. You could solve that particular problem, but I don't know on top of my head a solution for that. But it wouldn't be, for sure, it wouldn't be as negative as it is right now. I'm not sure though if it will go into tension or not. Probably you have to play with the equations a little bit to check that. Or you could also solve that with free FEM. That will tell you the solution right away. Yes?
A little conceptual question. So,
Yes.
but the stress intensity factors 2, 3, and -2, are those exact?
Yes, those are exact.
And that's in the condition of the cavity is significantly smaller than the
Correct. Yes. Yes. Here, you know, I'm drawing a rectangle around the cavity just to make it a little bit clearer. But I'm assuming this is in the far field. This is the far field. It's quite far away from the cavity. And you should be careful with that too, with your solution, your finite element solution, because if you put your boundaries too close, you will not get the analytical solution to match your solution. You need to place it far away so there is no influence of the boundaries in the stresses around the cavity. Yes?
So obviously in the third one, the tensile stresses would be the same no matter which direction it would be. But in the second one, is the tension there equal to the compression on the one that's facing the other direction?
No. Actually, this tension here is going to be equal to 1 delta sigma.
Okay, so it's just 1 delta sigma.
Yeah, for the tension.
Okay.
So this one is that one.
Yeah.
Okay? Actually, if you find a solution for this one, you will find that if this one is sigma theta theta, and here you have theta, and you start measuring theta from there, you will find that here it starts over here at negative delta sigma, and it goes like a sinusoid up to 3 delta sigmas.
Okay.
So the solution, that's why, again, in the Kirsch solution, you will see there is a cosine over here. So it's that harmonic component that's going to make that one vary.
So it goes from negative delta sigma to 3 delta sigma.
Yes. Okay, but here, we could have either compression or tension. Yes? I'm sorry.
The solution doesn't consider pore pressure
It-
around
It does not consider pore pressure around the wellbore, but actually there is a rigorous solution of pore elasticity for the wellbore, but everything you have to do if you were to consider pore pressure would be that this value inside here should be PW minus pore pressure, and all your stresses should be S1 minus pore pressure. Okay? So your sigma RR over here is going to be PW minus PP, and your sigma 1 and sigma 2 should be those. And that would be the way that you put pore pressure in it. All right, so play with the Kirsch equation, make it match with your numerical equation, and let's talk a bit about the problem of the fracture. Okay, for the fracture, there are two ways of solving that one, and I forgot to modify the question statement. So in the statement of the project, I'm asking you to create this is X, this is Y. I'm asking you to create an elliptical fracture right here. Okay? Let me fix that. It doesn't look like an ellipse. Something like this. And you could apply pressure inside this elliptical fracture, and in this case, you could just tell this boundary to not to move in Y direction, and you can tell this other boundary not to move in that other direction. And to have a pressure inside here, and that would be the end of the problem. However, there is another solution for that, which is actually easier than that. Here, you could assume that you're just working with half of the domain, and you could also work with a quarter, okay? But we're just going to do it with half. the lines here are not drawn to scale. Probably you want this section a little bit larger. But you could tell this boundary to not to move in this direction. And this is just a straight line. Also, you tell this boundary to not to move in this direction. And you have this one to not to move in direction y. And here you just apply a pressure. And from there, you measure your displacements and you measure your stresses in this region. So why do we not put confining far field stress in this case? In this case, we're using a concept which is called net pressure. The concept of net pressure says that, say that similar to the wellbore, if we have a far field in which you have a stress coming in this direction, sigma infinity, and inside a fracture you have a pressure PF which is higher than the far field stress, analyzing this problem is the same as analyzing a problem with no far field stresses and just putting a value here, which is the net pressure, where the net pressure is going to be the pressure in the fracture minus the far field stress. And this is what I'm asking you to do in this problem. A few more things. In the problem, there are several things I'm asking you. There is A, I think it's straightforward, then there is B, there is C, and there is D. So B is asking you just to compute, not to, from the numerical simulation, no analytical solution, to go here at the middle and measure in this line what is sigma xx. Number C asks you to compute the displacement here around that line, or if you were to do an ellipse as this one, you will measure the displacement of this boundary to the right and compare that. So, okay, this is B, this is C, and compare that to the analytical solution. You have an analytical solution for that, and it is this one over here. Okay? Watch out that here I'm using the axes which are not the same as the one in the problem. Okay? If you feel like doing this fracture 90 degrees and in next direction, just feel free to do that. Okay? But watch out with the equation. Use the right equation. And number D is, there is a mistake over here. So this one should be, and this is again because of copying and pasting, this one should be C divided by 2. I'm asking you to compute the stress at the tip of the fracture in this direction, in this line. It's outside the fracture. So this is A, B, C, D. And number E is to compare these results with the analytical equation. I'm not asking you to do that. That's not mandatory, okay? Because that equation is a little bit difficult to solve. It may take some time for that, for you to find that. But let me find it. I'll show you what it is. Actually, I never solved it myself, but Igor did, and it's not super complicated, but it takes some time. So let me find a paper here. Give me one sec. Let's find Igor. Here's Igor. And it should be this one. You go to equation number 20 in this paper. And that's the equation, okay? So if you feel like, solving this equation where J1 is a Bessel function over here, so it's a little bit longer than that, and this is the reference, you could do that, okay? The solution, you can, let's see if Igor has a solution. Okay, this is a solution, okay? And hopefully you will get something similar to what he has over there. Yes, Michael.
You stated explicitly what B, C, and D are. When you say plot results for part A,
yeah.
What are you just wanting, like a plot of that throughout the entire of those stresses throughout the entire?
Well, no. Yes. For A, it says plot results. I like to see an XY scalar map solution of that. So a field contour map of that.
Okay,
That's what I like to say. A colorful,
contour.
solution of stresses around the cavity.
So then that would be 3 plots, one for each of the
So
each of the stresses.
A, yes, correct. So these ones are going to be these colorful plots, right? Where you have the domain, you have your cavity, and things change like around here with nice colors, something like that. And all these others are XY plots, where you have data points and you have your analytical solution on top of that. Yes, because they're along a line. The other one is a map for an XY.
I just wanted to double check.
Yeah. Yeah, that's it. All right. So, yeah.
For the
John.
Walmart problem,
Yeah.
the 2 parts were plotting stress in one line.
Yeah.
Do you want the same XY plot, or do you also want like contour maps for this?
No, just I want XY plots only. Yeah.
What about part A?